Hello, everyone, and welcome to this session. I'm here with Angelo Tulumello, who is a PhD candidate at the Tor Vergata University in Rome, and also works as a network software engineer at Axbrid in Italy, I assume. Um, welcome, Angelo. And he has participated in several international projects funded by the European Union during his career. And his main research interests are programmable networks, and that's why we have him here. But he has a specific focus. He had a specific focus on SRv6, P4, eBPF, and stateful programmable data planes. And I believe this is the topic of his presentation today. Stateful programming is going to talk about an extension to P4 to implement scalable stateful processing. So, Angelo, please take the floor and go ahead.
Thanks for the presentation. Yes, in fact, today I am presenting this work with the title Extending P4 to realize a scalable flow caching mechanism. This is a project that we did with Marco Bonola and Salvatore Pontarelli, also from Axbrid, and Matti Kadush and Jonathan Pietzky from NVIDIA Networking. Okay, so we know that programmable data planes bring the flexibility to reprogram the protocol parsing and match action tables in switching ASICs. Moreover, in the last few years, programmable data planes reached the technological and industrial maturity by providing line rate processing at terabit speeds. And P4 is emerged as the de facto standard for how to program programmable data planes. So a further step to enhance the programmability is the addition of primitives that implement stateful functions directly in the data plane. So this will involve some internal states in the switching ASICs. So this is for sure not an easy task. One of the problems that we have when implementing stateful functions in the data plane is that the stateful network functions usually employ heavy state information, while the switching ASICs have limited hardware resources, like, for example, the SRAM capacity for the tables. Anyway, an increasing number of research works is proving its feasibility. So with this work, we want to propose programming abstractions for stateful network functions. And we do this by adding some elements to the P4 language. Okay, going a bit in detail, this was a joint work with NVIDIA Networking, whose main goal was to understand the stateful primitives to be included in future NVIDIA hardware, and most importantly, how to program them. So we started by defining a pool of reference use cases. So for example, the stateful firewall, the flow caching mechanism that we are going to see in this presentation, dynamic NAT, and so on. And then we derived the functional and architectural requirements, always keeping in mind the hardware capabilities, so the hardware features that we have. Then we defined the P4 language extensions, and we extended the software switch behavioral model, the BNV2, prototype to have a functional prototype of these stateful extensions. Then we extended we validated these use cases implementation in this extended BNV2. Okay, now I will give an idea of the main building blocks of these P4 extensions with a simple use case. So we consider a very simple, basic stateful firewall. So we have a stateful switch that is connecting a LAN network, so a local area network, with a DMZ. So the firewall wants to enforce that for all the packets that are originated from the LAN must be forwarded to a server in the DMZ. Also, the responses from the servers must be forwarded to the local area network, but only if that flow was initiated from the LAN. Instead, for flow that are initialized from the DMZ, the stateful switch must drop the packets. Okay, so to implement this function, we need mainly two features. So first, we want to define what are those flows, so how to identify the flows. We do this by defining the flow keys. So in this specific case, we have a bidirectional flow key, because for packets coming from the LAN, we take the 5-tuple, so the IP source and destination addresses, and layer 4 source ports and destination ports and protocol. And then for the opposite direction, what the switch will extract is the flow key, but the 5-tuple, but swapping the IP addresses and swapping the layer 4 ports. Okay, then the second element that we need is a table that we call the flow context table that associates the flow key, a given flow key, to the state, so to some internal memory that is associated to a flow. Okay, so let's imagine the first packet of a new flow from a client in the LAN. So the flow key is added in the flow context table, and the state is updated, and this state is, for example, set to open. So the response of this packet, so that has the same flow key from the DMZ, matches and so finds the flow key inside the flow context table, and so it is allowed to be forwarded to the client that originated the request. Instead, if a new flow with a different flow key is initiated from the DMZ, we don't have this flow in the flow context table, and so the packet is dropped. Okay, again, as an example, here is the implementation with the before extended code of this use case. So here displayed, we see the ingress pipeline control block, and the first element is the stateful table, that is the core element of these new extensions. So it is a match action, an exact match action table, and it matches on the fields defined on the flow keys. So in this case, we have two flow keys for the reason I said before, so that we want bidirectional flow keys. And you can see in the apply block that we can select which flow key to apply to the stateful table based, for example, in this case, based on the ingress port on which the packet was received. Okay, then we have a reference to the state context, and the state context is a data structure that contains the definition of all the states associated to a flow. So in this case, we just have one field that is the state field, but we can have an arbitrary number of fields definition. Okay, then, for example, we can configure an eviction policy that in this case can be the least recently used, or for example, the least frequently used, that is implemented inside the target. And then we have a reference to the graph. Okay, the graph, state graph, is a special control block, and it is the only control block that can read and write the state context associated to a flow. And then in this control block that has a similar syntax with respect to the before parser, we have the state transition, so how the network function must behave. So for example, here in state start, we have that if the packet ingress port is the LAN, we transition to the state established. Else, if the ingress port was the NZ, we drop the packet. Then is state established. So if the packet, if the next packet matches a state that is established, what we have is that in both directions we forward the packet to the correct output port. Okay, now I will present the flow cache use case, and this use case can be found in the repository displayed here in the bottom. The flow cache use case implements a flow caching mechanism so that the stateful switch can handle directly in the data plane the encapsulation of top talker flows. So in this topology, we have a data center network on the right, which has several tenants that are in the VXLAN domain. So these tenants can request services to some bare metal application that instead run on on the VLAN IP domain. So in a real scenario, to handle we would have to handle millions of entries to support all the tenants in a data center network. So we employ another network device that is this low path, in which we have the large connection table. So this network device is the OTR. It is displayed here in the left. Okay, now let's see the operation of this use case. So imagine we have the first request from a tenant in the data center network. So this first request is received by the stateful switch that applies a stateless entry. So it just decapsulates and forwards to the correct bare metal application the packet. Then the bare metal application replies with response, and the stateful switch will forward this response to the overlay tunnel router, because it doesn't know how to encapsulate the packet to send the request back to the response back to the tenant. Then the OTR encapsulates the packet, well, reads the information from the large connection table and encapsulates accordingly the packet. And then this packet reaches the stateful switch that will learn the VXLAN encapsulation. So the information that is encoded inside this packet saves the entry related to this flow inside the flow cache, and then sends the packet back to the data center network. Okay, now for the second request, as before, the stateful switch will forward the packet to the bare metal application, and then the response in this case, since the entry was cached before with information received by the OTR, the stateful switch can on its own encapsulate the packet and send it back to the data center network. Okay, in this use case could arise an out of order problem. So let's think about of 3 packets from the bare metal application to the stateful switch. So the first packet goes inside the OTR. Then the OTR processes the packet and encapsulates it to the stateful switch. So the stateful switch adds the entry in the cache, and the second packet is being processed inside the OTR. Now, it could happen that the third packet, for example, arrives to the switch before the OTR finished its processing on packet 2. And so it will, we will have out-of-order packets. Okay, so to solve this issue, what we do is that we maintain a packets in flight counter for each flow, and we continue sending packets to the OTR until this packets in flight counter is 0. So when we don't have any more packets inside the OTR, we can start to actually apply the encapsulation, and so the stateful flow caching mechanism. Okay, here it is a brief demo that demonstrates this application. Okay, so this is an emulated environment made with the Linux namespaces. So we have the stateful switch namespace, the data center one, the servers, and the OTR namespaces. Okay, so first of all, we start the extended BMV2 software switch, and then we insert the stateless flow entry that is needed to forward the traffic from the data center network to a specific server. Okay, so packets from the data center to bare metal server will be de-encapsulated with this entry. Then we will insert a VLAN tag and we forward the packet to the bare metal application. So now in the OTR namespace, we run a simple Python script that is emulating the OTR functionalities. Now in the server's namespace, we run a simple netcat server that is waiting for incoming connections. And then we emulate a tenant request by initiating a connection with netcat from a tenant. Okay, so now we can see here that the OTR has received the packet from the stateful switch and responded with the VXLAN encapsulated one. So here we can see that the connection is established and there is exchange of messages. Okay, now we open the packet traces captured in the OTR and data center links. Okay, in the OTR capture, we can see that the first packet is de-encapsulated, so it doesn't have the VXLAN, while the second is the correctly VXLAN encapsulated one by the OTR. Now we see the live capture on the server side. Okay, in this capture, we can see the whole connection between the tenant and the bare metal application. And so after the first packet from the OTR, the switch has actually learned the VXLAN information, has stored it as an entry inside the flow cache. Okay. Okay, so to conclude, with this work, we defined the P4 language extensions to define a new programming abstraction that is just tailored to define stateful network functions. We implemented this prototype in BMV2 and we assessed, from a functional point of view, a set of real-world use cases. So for next steps, we still miss the front-end compiler because we configured the BMV2 implementation by modifying the JSON output of the applications. Then we have to investigate the support for other use cases that may require different functionalities, for example, in network computation. And then map the language extensions to the hardware design, so to the actual ASICs. Okay, thanks for your attention.
Thank you very much, Angelo. This was an excellent presentation. I think it was the topic was very interesting, and you really gave very good examples. I have a question. At the end, you mentioned that you are working on the back end to compile these on a target. Is there a specific target architecture for which these proposed constructs fit particularly well? A target architecture which this fits particularly well.
The target architecture for these extensions were the V1 model, let's say. So the one with ingress pipeline, egress pipeline, and checksum verification. Anyway, we can say that most of the functionalities are implemented in the ingress pipeline. So every target that has, let's say, an ingress pipeline could fit with these extensions.
Okay, that's great. Yeah, that's great. And so, talking about that, you said this fits to any target that has that follows the V1 model. So, if you look at the P4 language, there are already mechanisms to store state, right? Like registers, or Andy has presented in the P4 workshop, and the Fingerhut has presented in the P4 workshop work that is being done in the context of the portable NIC architecture to add tables where entries can be added dynamically by the data plane. I don't know if you're aware of it, but in any case, so there are other methods to have stateful flow tables, which is one of the constructs that you have introduced. The other one is the idea of state graphs, which doesn't exist in P4 currently. But one could argue you could support these use cases using the existing constructs in P4. So my question is, can you explain why is it more advantageous to use the constructs that you have proposed, the state graphs and the stateful tables versus the ones that are already in P4?
Okay, so the first reason that I can imagine is that in the state graph you have clear where you can update the states. Okay, you have a block of code in which you are allowed to update the states. Okay, we know that there are several problems. We cannot touch the states everywhere in the pipeline. So these could be one reason. But the second reason maybe could be the fact that stateful protocol, stateful network function, especially, for example, layer 4 protocols, employs state machines. Okay, we think that a state machine abstraction is advantageous for the expressiveness of programming stateful network functions. So this could be the second.
Yeah, you're right. I mean, I agree with you. It makes a lot of sense. So are you guys planning on to proposing these extensions within the P4 community, like within the P4 design language group or some of the architectural groups?
If there's interest in this direction, and I think that the interest is increasing and the last years and the last months. I think that yes, we would like to push these extensions, and not because always more stateful functions are being implemented in P4, for example. But we always must remember that P4 is I think it's the perfect abstraction for match action tables, okay? And it perfectly describes what a switching ASICs that has a pipeline of match action table has to do. Anyway, stateful network functions have a slightly different abstraction for what we think.
Good point. Yes. Yeah. So I guess having given this presentation at the P4 workshop is probably a good way to gauge whether there is interest, and then hopefully there is, because I think this is an interesting idea, and then you can bring it up in one of the work groups. Angelo, thank you very, very much. It was a really interesting work and presentation, and
Thank you, Mario.